Welcome! In this session, we'll explore the problem number 167, twosome two-input array is sorted. This is a classic algorithmic problem that tests your ability to implement efficient solutions for finding two numbers that add up to a target value in a sorted array. Let's dive in and break it down step by step. The problem requires us to work with a one-indexed array, which means counting starts from 1 instead of the traditional 0-based index. The array, numbers, is already sorted in non-decreasing order, and our job is to find two numbers within this array that add up to a given target value. The output should be a pair of indices, index 1, index 2, such that the first index is smaller than the second, and both indices are within the bounds of the array. Importantly, we know from the problem that there is exactly one solution, meaning we don't have to handle cases where no solution exists. Additionally, we need to ensure our algorithm is efficient, with a runtime complexity better than O, in superscript 2, which excludes a brute force approach that checks every possible pair. This requirement encourages us to think of a more optimized solution, leveraging the fact that the array is sorted. To illustrate how this works, let's examine the first example. Here, the input array is numbers equals 2, 7, 11, 15, and the target is 9. We need to find two numbers in the array that add up to 9. Looking at the elements, we see that 2 at index 1 and 7 at index 2 satisfy this condition because their sum, 2 plus 7, equals the target 9. Therefore, we return 1, 2 as the solution. Notice how the indices are 1-based, not 0-based, which aligns with the problem requirements. This demonstrates how the solution format works in practice and reinforces the importance of identifying the correct pair of numbers efficiently. In the second example, the input array is numbers equals 2, 3, 4, and the target is 6. Following the same logic as before, we observe that the number 2 at index 1 and the number 4 at index 3 add up to the target, since 2 plus 4 equals 6. As a result, the output is 1, 3. This example further highlights how we need to carefully check for pairs of numbers that sum to the target while adhering to the constraints of one-based indexing. Then, in the third example, we have numbers equals -1, 0, with a target of -1. Here, the numbers -1 at index 1 and 0 at index 2 meet the condition because their sum, -1 plus 0, equals the target. So, the output is 1, 2. These examples emphasize the precision required in identifying the correct indices and ensuring the output format is consistent. Now that we've seen the examples, let's summarize the constraints and edge cases we need to consider. The array has a minimum size of 2 and a maximum size of 30,000, which means our solution must handle very large input efficiently. Each number in the array and the target value can range from -1000 to 1000, so we must account for negative values as well. The fact that the array is sorted in non-decreasing order is a key advantage, as it allows us to use optimized approaches like the two-pointer technique. Additionally, the guarantee of exactly one solution simplifies the problem since we don't need to handle cases with no valid pairs. Edge cases to consider include small arrays, arrays with duplicate values, and scenarios where negative numbers are involved. These constraints and edge cases ensure our solution is robust and performs well across a variety of inputs. To solve the twosome two problem, let's start by exploring different approaches. The first method we can consider is the brute force approach. The intuition here is straightforward. Since we need to find two numbers in the array that add up to the target, we can simply try every possible pair of numbers. To implement this, we use two nested loops. For each pair of indices, we check if the sum of the numbers equals the target. If it does, we return their indices in a one-indexed format. However, this method has a time complexity of O(n squared) because of the nested loops, and it uses constant space, O(1). While this approach is simple and easy to understand, it's highly inefficient for large arrays and doesn't take advantage of the fact that the input array is sorted. This brings us to our optimized solution, the two-pointer approach. The two-pointer approach leverages the fact that the input array is sorted. Here's the key idea: we start with 2 pointers, one at the beginning of the array and the other at the end. By examining the sum of the numbers at these two positions, we can determine how to adjust the pointers to efficiently find the target sum. If the sum of the two numbers is less than the target, it means we need a larger sum, so we move the left pointer to the right. If the sum is greater than the target, we need a smaller sum, so we move the right pointer to the left. If the sum matches the target, we return the indices of the two numbers in a one-indexed format. This logic is not only simple but also highly efficient for this type of problem. Now let's analyze the efficiency of the two-pointer approach. In terms of time complexity, it only takes n, since each pointer moves at most n steps. For space complexity, it's 1, because we aren't using any additional data structures. This makes the two-pointer approach both efficient and memory-friendly. Compared to other methods, it's also easier to implement and debug. However, there's another approach worth mentioning, the binary search method. Here, for each element in the array, we use binary search to find its complement, the value required to reach the target. While this also takes advantage of the sorted property, it involves a slightly more complex implementation. Specifically, for each number, we perform a binary search on the remaining part of the array. This results in a time complexity of n log n, which is less efficient than the two-pointer method. The binary search approach has a time complexity of n log n, and a space complexity of 1, similar to the two-pointer approach in terms of memory usage. However, it's slightly slower overall because of the repeated binary search operations. While binary search can be a good option in some scenarios, it introduces additional complexity compared to the two-pointer technique. With all these considerations in mind, the two-pointer approach stands out as the optimal solution for this problem. It's efficient with a linear time complexity of n, simple to implement, and fully leverages the sorted nature of the array. In contrast, the brute force method is far too slow, and the binary search approach, while faster than brute force, doesn't match the simplicity or speed of the two-pointer method. The two-pointer approach does come with some trade-offs, though. It assumes that the input array is sorted. If the array isn't sorted, you'd need to either sort it first or use a completely different approach, such as hashing, which works well for unsorted arrays. Despite this limitation, for problems where the sorted property can be leveraged, the two-pointer technique is the best choice. It strikes the perfect balance between performance and simplicity, making it the ideal solution for this problem. By using this approach, we achieve an efficient and elegant solution that is both easy to implement and highly effective for large datasets. To solve the 2-sum-2 problem, we are tasked with finding two distinct numbers in a sorted array that add up to a given target value, and then returning their indices. If no such pair exists, we signal this by returning an empty list. The brute force approach is the most straightforward method to tackle this. It involves checking every possible pair of numbers in the array to see if their sum matches the target. First, we validate the input to ensure that the array contains at least two elements. If not, we return an empty result. Then, we use an outer loop to iterate through the array starting from the first element and stopping at the second to last to ensure each iteration has a pair to check. Inside this outer loop, we use an inner loop to check all subsequent elements after the current one, ensuring unique pairs are considered. This approach guarantees thoroughness but can be computationally expensive due to nested iterations, as we'll discuss shortly. In the brute force approach, for each element at index I, we iterate through all the elements that follow it in the array using a second index j. This ensures we only check unique pairs, avoiding duplicates or reversed pairs like a_i, a_j, and a_j, a_i. For every pair, nums, I, nums, j, we check if their sum equals the target value. If it does, we immediately return the indices, I, j, as the problem requires finding just one valid pair. If no such pair is found after all iterations, we return an empty list to indicate no solution exists. For example, if the input is nums equals 2, 7, 11, 15, and target equals 9, we start with the first element, 2 at index 0, and check it against the next element, 7 at index 1. Their sum equals 9, so we return 0, 1. While simple and intuitive, this approach has a time complexity of n squared, due to the nested loops, making it inefficient for large arrays. However, it doesn't require extra space, resulting in a space complexity of 1. We can optimize the solution using a hash map to reduce the time complexity. The intuition here is to use the hash map to store the complement of each number with respect to the target while iterating through the array. This allows us to check in constant time if the complement of the current number already exists in the hash map. To begin, we initialize an empty hash map, scene, which will store numbers as keys and their indices as values. Then, we iterate through the array, and for each element, we calculate its complement using the formula complement equals target number. If the complement is found in the hash map, we immediately return the indices seen, complement, I. Otherwise, we store the current number and its index in the hash map, so it can be used for future complement checks. This approach ensures that each element is processed only once, eliminating the need for nested loops. If the hash map approach completes the loop without finding a valid pair, we return an empty list to indicate no solution exists. Let's walk through an example. Consider the input nums equals 2, 7, 11, 15, and target equals 9. We start with the first element, 2 at index 0. The complement is 9 2 equals 7, which is not in the hash map yet, so we store 2 at index 0 and seen, resulting in seen equals 2 o'clock. Next, we move to the second element, 7 at index 1. The complement is 9 7 equals 2, and this time, 2 is found in the hash map at index 0. Therefore, we return the indices 0, 1. This approach has a time complexity of O, n, as each element is processed once, and a space complexity of O, n, due to the hash map. It's significantly faster than the brute force method for large arrays, making it a more practical solution. The hash map approach not only improves efficiency but also handles edge cases effectively. For instance, if the input array has fewer than 2 elements, we immediately return an empty list, as it's impossible to find a pair. If no pairs sum to the target after processing the entire array, we also return an empty list. Negative numbers are seamlessly handled since addition and subtraction work consistently for them. Duplicate elements in the array are managed by ensuring the hash map stores indices distinctly, preventing self-pairing unless explicitly allowed by the problem constraints. Comparing the two approaches, the brute force method uses no additional data structures and relies only on the input array, whereas the hash map approach trades additional space for significant speed improvements. The pseudocode for the hash map solution is straightforward: initialize an empty hash map, iterate through the array, calculate the complement, check for its existence in the hash map, and store the current number and index if needed. In summary, the hash map approach is a major improvement over the brute force method, reducing time complexity from O, n squared, to O, n, by leveraging efficient lookups. It is particularly well suited for large arrays, where performance gains are most noticeable. Additionally, it handles edge cases like small arrays, negative numbers, and duplicates effectively, ensuring correctness in all scenarios. By trading a small amount of space for speed, this approach demonstrates how thoughtful use of data structures can optimize algorithms. For problems like 2sum2, understanding and applying such techniques can make a significant difference in both efficiency and scalability. This Python implementation solves LeetCode problem number 167, 2sum2 input array is sorted, using the two-pointer technique, which is optimal for sorted arrays. The algorithm works as follows. 1. Initialize 2 pointers, the left pointer starts at the beginning of the array, index 0, and the right pointer starts at the end of the array, len, numbers, 1. 2. Iterate while pointers do not cross. The core logic is in a while loop that continues as long as left-right. This ensures that we are processing valid pairs of numbers from the array. 3. Calculate current sum. At each step of the loop, compute the sum of the numbers at the left and right pointers, current underscore sum. For check if current sum matches target, if current underscore sum equals the target, return the 1-based indices of the left and right pointers as left plus 1, right plus 1, since the problem specifies 1-based indexing. If current underscore sum is less than the target, increment the left pointer to move to a larger value in the sorted array, which will increase the current underscore sum. If current underscore sum is greater than the target, decrement the right pointer to move to a smaller value, which will decrease the current underscore sum. 5. Handle edge cases. If no pair is found by the time the loop ends, return an empty list, to indicate no solution exists. This approach runs in O, n, time complexity because each pointer moves at most once through the array. The space complexity is O, 1, since no additional data structures are used. This makes the solution efficient and well suited for large input arrays. This is the Java implementation of LeetCode problem number 167, 2sum2 input array is sorted. The logic mirrors the Python implementation, using a two-pointer approach to efficiently find the two indices such that the sum equals the target. Key differences include explicit type declarations, use of arrays instead of lists, and Java's class structure. The algorithm operates in O(n) time complexity by narrowing the search space from both ends of the sorted array. Here, we start with an example where the input array is numbers equals 2, 7, 11, 15, and the target is 9. First, we initialize two pointers, left at index 0 and right at index 3, which correspond to the first and last elements of the array. The goal is to find two numbers in the array that sum up to the target value, 9. In step 1, we calculate the sum of the numbers at the left and right pointers, 2 plus 15 equals 17. Since this sum is greater than the target, we move the right pointer one step to the left, reducing the range to consider smaller sums. Now, in step 2, the new sum is 2 plus 11 equals 13, which is still greater than the target, so we again move the right pointer leftward. Finally, in step 3, the sum becomes 2 plus 7 equals 9, which matches the target. At this point, we return the 1-based indices, 1, 2, as the solution, since these indices correspond to the two numbers that sum to the target. In this example, the input array is numbers equals 1, 3, 4, 5, 7, 10, and the target is 8. As before, we initialize left at index 0 and right at index 5. The goal remains the same, find two numbers that sum to the target value. In step 1, we compute the sum of the numbers at the left and right pointers, 1 plus 10 equals 11. Since the sum is greater than the target, we reduce it by moving the right pointer one step to the left. Now, the right pointer is at index 4, and in step 2, the new sum is 1 plus 7 equals 8. This time, the sum matches the target, so we return the 1-based indices, 1, 5, as the solution. This demonstrates how adjusting the pointers helps us efficiently narrow down the correct pair of numbers. In this example, the input array is numbers equals 1, 2, 3, 4, 4, 9, and the target is 8. Again, we initialize left at index 0 and right at index 5. In step 1, we calculate the sum of the numbers at the pointers, 1 plus 9 equals 10. Since the sum is greater than the target, we move the right pointer leftward to decrease the sum. Now, the right pointer is at index 4, and in step 2, the new sum becomes 1 plus 4 equals 5. Since this sum is less than the target, we move the left pointer rightward to increase the sum. With left now at index 1, step 3 gives us a new sum of 2 plus 4 equals 6, which is still less than the target. So, we again move the left pointer rightward. Next, in step 4, the sum becomes 3 plus 4 equals 7, which is still less than the target, so we move the left pointer rightward once more. Finally, in step 5, the pointers are at indices 3 and 4, and the sum of the numbers at these positions is 4 plus 4 equals 8, which matches the target. At this point, we return the 1-based indices, 4, 5, as the solution. This example highlights how the two-pointer method can handle cases where duplicate numbers appear in the array, ensuring that we still find the correct pair efficiently. The time complexity of this solution is derived from the two-pointer approach. Since the input array is sorted, we can initialize two pointers, one at the beginning and one at the end of the array. This initialization step is an O(1) operation because it involves setting two variables. The core of the algorithm lies in the while loop, which runs as long as the left pointer is less than the right pointer. In each iteration, we calculate the sum of the elements pointed to by these two pointers, check if it matches the target, and adjust the pointers accordingly, either incrementing the left pointer or decrementing the right pointer. Each of these steps, including the sum calculation and pointer adjustments, is performed in constant time, or O(1). Since the pointers traverse the array from opposite ends and meet in the middle, the loop executes at most n iterations, where n is the length of the input array. Finally, when the target is found, the return statement simply constructs a list of the two indices, which is also an O(1) operation. This gives us an algorithm with linear time complexity overall, dominated by the O(n) iterations of the while loop. The total time complexity of the algorithm is therefore O(n), as each element of the array is processed at most once during the while loop. Turning to space complexity, the algorithm uses only a constant amount of extra memory. The variables left, right, and current_sum are simple scalar variables, requiring O(1) space. The output, which is a fixed-size list containing two integers, also uses O(1) memory. Importantly, no additional data structures, such as hash tables or auxiliary arrays, are needed for this solution. Therefore, regardless of the size of the input array, the overall space complexity remains O(1), making this algorithm highly efficient in terms of memory usage. To better understand the time complexity, let's analyze the best, average, and worst-case scenarios. In the best case, the target sum is found in the first iteration of the while loop. Here, the algorithm exits immediately, resulting in constant time complexity, or O(1). In the average case, the target is located after processing approximately half the array, which means the loop iterates about n/2 times. However, in big O notation, constants are ignored, so the average case is still O(n). In the worst case, the loop processes all n elements of the array either because the target is found at the very end or because no solution exists. Even in this situation, the time complexity remains O(n), as the loop iterates a maximum of n times. Let's compare this optimized two-pointer approach to the brute force method. The brute force approach involves iterating through all possible pairs of elements in the array to check if their sum equals the target. Since there are approximately n times, n1, divided by 2 pairs, this results in a time complexity of O(n squared). However, it uses no additional data structures, so its space complexity is O(1). On the other hand, the two-pointer approach dramatically reduces the time complexity to O(n), as it processes each element at most once. Like the brute force method, the two-pointer approach also has a space complexity of O(1), because it does not rely on any auxiliary data structures. This makes the two-pointer method significantly faster and more scalable for larger inputs, while maintaining minimal memory usage. To mathematically validate the time and space complexity, let's examine the operations step by step. For time complexity, the while loop performs constant time operations such as comparisons, sum calculations, and pointer updates during each iteration. Since the loop runs at most n times, where n is the size of the input array, the total time complexity is O(n). For space complexity, the algorithm uses a fixed number of variables, including left, right, and current_sum, as well as the return value, which is a two-element list. The memory usage does not scale with the size of the input array, meaning the space complexity is constant, or O(1). This rigorous analysis confirms the efficiency of the two-pointer approach in terms of both time and space. When solving this problem, there are several common mistakes to watch out for. First, in the brute force approach, failing to handle duplicate pairs can lead to redundant computations. For example, iterating over both A_i, A_j, and A_j, A_i unnecessarily duplicates work. Next, edge cases with negative numbers or zeros are often overlooked. If the target is 0, you need to correctly handle scenarios like finding 2 zeros in the array. Another issue arises with hash maps in optimized solutions. Forgetting to check for existing entries before adding new elements can cause incorrect outputs or key collisions. Additionally, some solutions ignore input size constraints, relying on O(n squared) approaches, which will fail for larger arrays where n can be as large as 10 to the power of 5. Lastly, misinterpreting the problem requirements, such as confusing indices with values, can lead to incorrect results even if the algorithm itself is correct. Being mindful of these pitfalls can save you time and ensure accuracy in your solution. Now, let's talk about some key insights that can help during interviews. Recognizing patterns is crucial. Many problems boil down to finding pairs, subsets, or combinations that satisfy a condition. Knowing when to use techniques like hash maps or two-pointer approaches can drastically reduce complexity. Efficiency is also highly valued in interviews. While brute force solutions may work, showing progression to more optimal solutions, like moving from O(n squared) to O(n), demonstrates your understanding. Clear communication is another critical skill. Always clarify edge cases with the interviewer, such as how to handle empty arrays, single-element arrays, or duplicates. Finally, explaining the trade-offs between approaches is just as important as solving the problem. For example, if you're comparing a sorting and two-pointer approach versus a hash map solution, discuss the trade-offs between time complexity and space usage. Knowing these related problems, like 2-sum, 3-sum, for sum, and subarray sum equals k, can also help you identify patterns and extend your knowledge to similar challenges. Next, let's examine some alternative approaches. One common method is the two-pointer approach, which works well after sorting the array. This achieves O, n log n, for sorting in O, n, for the two-pointer traversal, making it efficient in terms of time complexity. However, it's important to note that this approach loses the original indices, which may be required in some problem variations. Another approach is the one-pass hash map technique. By storing the difference between the target and the current element as you iterate, this method achieves O, n, time complexity, but it does require extra space for the hash map. Finally, there's the brute force approach, which involves checking all possible pairs. While simple to implement, it has a time complexity of O, n squared, making it impractical for larger inputs. However, it can still be a valid fallback for smaller arrays. Each of these approaches has its own trade-offs, so understanding their strengths and weaknesses will allow you to choose the best one for a given situation. Great job! To wrap up, we used the two-pointer technique to efficiently solve this problem with optimal time and space complexity. Remember to practice similar problems to strengthen your understanding. Thanks for joining, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!